So before we start playing with our shiny new Elasticsearch server, let's go over some basics of Elasticsearch first so we understand the concepts of how it works, what it's all about, how it's architected, and when we're done with that, we'll have a quick little quiz to reinforce what you learned. After that, we'll start messing around with it. So there are three main logical concepts behind Elasticsearch. The first is the document. So if you're used to thinking of things in terms of databases, a document is a lot like a row in a database. It represents a given entity, something that you're searching for. And remember, in Elasticsearch, it's not just about text. Any structured data can work. Now, Elasticsearch works on top of JSON formatted data. If you're not familiar with JSON, it's basically just a way of encoding structured data that may contain strings or numbers or dates or what have you, in a way that you can actually transmit it across the web cleanly. And you'll see a ton of examples of this throughout the course, so it'll make more sense later on. Now, every document can have a unique ID, and you can either explicitly assign a unique ID to it yourself, or allow Elasticsearch to assign it for you. And it also has a given data type that describes what sort of thing this document is. So for example, you might have documents that represent encyclopedia articles or documents that represent log entries from your web server. And that's where the concept of types comes in. So you can have many documents that belong to a given type. And a type is basically a schema or a mapping shared by a bunch of documents. So for example, you might have a type that defines what an Apache access log entry looks like. And that might define a mapping that says an Apache access log contains things like a request URL and a status code and a request time and a referring URL and things like that. Or you might have a type that represents an encyclopedia article, for example, that represents things like the text of the article itself, the author of the article, the date the article was written, whatever else there might be, the title of the article. So you can think of a type as a schema. And again, if you take this back to a database analogy, it's a lot like a table, where you define the individual columns that are in a given row or a document in our terminology. Finally, there's the concept of an index, which is a collection of types, and it is basically an entity that you can search across. So if you need to search across multiple different types potentially, then you'd want to make sure that all those types are contained within the same search index. So an index is sort of the highest level entity that you can query against in Elasticsearch. And it can contain a collection of types, which in turn contain a collection of documents. So again, bringing this back to an analogy of a database, you can think of an index as a database, a type as a table, and a document as a row. Those are kind of the analogies there of database to Elasticsearch world. Now, of course, it's not quite that simple. Basically, what is an index? Well, an index is actually what's called an inverted index, and this is basically the mechanism by which pretty much all search engines work. So the idea is that if I have a couple of documents, let's assume they just contain text data here. Let's say I have one document that contains space, the final frontier, these are the voyages. And maybe I have another document that says, he's bad, he's number one, he's a space cowboy with a laser gun. And if you understand what both of those are references to, then you and I have a lot in common. Now, an inverted index wouldn't store those strings directly. Instead, it flips it on its head. So what it does in a search engine is it actually splits each document up into its individual search terms. And in this example, we'll just split it up for each word, and we'll lowercase them just to normalize things. And then what it does is it maps each search term to the documents that those search terms occur within. Okay, so in this example, the word space actually occurs in both documents. So my inverted index would indicate that the word space occurs in both documents 1 and 2. The word the also appears in both documents, so that will also map to both documents 1 and 2. And the word final only appears in the first document. So our inverted index would map the word final, the search term final, to document 1. Now, it's a little bit more complicated than that in practice, and in reality it actually stores not only what document it's in, but also the position within the document that it's in, so we can do things like phrase search and stuff like that. But at a high conceptual level, this is the basic idea. An inverted index is what you're actually getting with a search index, where it's mapping things that you're searching for to the documents that those things live within. And of course, it's even not quite that simple. So how do I actually deal with the concept of relevance? Let's take, for example, the word the. How do I deal with that? So the word the is going to be a very common word in every single document. So how do I make sure that only documents where the is like a special word are the ones that I get back if I actually search for the term the? Well, that's where TF-IDF comes in. That stands for term frequency times inverse document frequency. It's a very fancy sounding term, but it's actually a very simple concept. So let's break it down. Term frequency is just how often a given search term appears within a given document. So if the word space occurs very frequently in a given document, it would have a high term frequency. Or if the word the appears frequently in a document, it would also have a very high term frequency. Now, document frequency is just how often a term appears in all of the documents in your entire index. So here's where things get interesting. So the word space probably doesn't occur very often across the entire index, so it would have a low document frequency. However, the word the does appear in all documents very frequently, so it would have a very high document frequency. So when we divide term frequency by document frequency, and that's the same as multiplying by the inverse document frequency mathematically, we get a measure of relevance. So we see how special is this term to this document. It measures not only how often does this term occur within this document, but how does that compare to how often this term occurs in documents across the entire index. So with that example, the word space in an article about space would rank very highly. However, the word the wouldn't necessarily rank very highly if that's a common term found in every other document as well. And this is the basic idea of how search engines work. If you're searching for a given term, it will try to give you back results in the order of their relevancy, where relevancy is loosely based at least on the concept of TF-IDF. Got it? It's really not that complicated. So how do you actually use an index in Elasticsearch? Well, there's three ways we can talk about. One is the RESTful API. Now, if you're not familiar with the concept of REST queries, let me explain it at a very high level. It's just like how you request a web page from a web server from your web browser on your desktop. So when you're requesting a web page on your browser, like from Chrome or whatever you use, what's happening is that your browser is sending a REST request to a web server somewhere. And every REST request has a verb, like get or put or post, and some sort of body that specifies what it is that you want to get back. So for example, if you're looking for a web page, you would send a REST query for a get verb, and then that get would request a specific URL that you want to retrieve from that web server. Now Elasticsearch works exactly the same way, over the same HTTP protocol that web servers work across. So this makes it very easy to talk to from different systems. So for example, if you were searching for something on Elasticsearch, you would issue a GET request through a REST API over HTTP, and the body of that GET request would contain the information about what it is you want to retrieve in JSON format. And we'll see examples of this later on. But the beautiful thing about this is that if you have a language or an API or a tool or an environment that can handle HTTP requests, like just talking to the web normally, then it can handle Elasticsearch. You don't need anything beyond that. If you understand how to structure the JSON requests for Elasticsearch, then any language that can talk to HTTP can talk to Elasticsearch. And most of this course is going to focus on doing it that way, just so you understand how things work at a lower level and what Elasticsearch is capable of under the hood. But you don't always have to do it the hard way. If you are accessing Elasticsearch from some application that you're writing, like a web server or a web application or whatever it is, often there will be client APIs that provide a level of abstraction on top of those REST queries. So instead of trying to figure out how do I construct the right JSON format for the type of search that I want or inserting the kind of data that I want, there's a lot of client APIs out there that make it easier for you and just have specialized APIs for searching for things and putting things into the index without getting into the nitty-gritty of constructing the actual request itself. So whether you're using Python or Ruby or Perl or C++ or Java, there are APIs out there that you can just use. Finally, there are even higher level tools that can be used for analytics, and one that we'll look at in this course is called Kibana. It's part of the larger Elastic Stack. And that is a web-based graphical UI that allows you to interact with your indices and explore them without writing any code at all. So it's really more of a visual analysis tool that you can unleash upon pretty much anyone in your organization. So in order of low-level to higher-level APIs, there are RESTful queries that you can issue from whatever language you want. You can use client APIs that make things a little bit easier, or you can just use web-based UIs to get the information you need as well. So those are the basic concepts of how Elasticsearch is structured and how you interface with it. With that under our belt, we can talk more about how it works under the hood and how its architecture works.